Chapter 13, Confidence Intervals. Section 13.1, Using and Interpreting Confidence Intervals. A confidence interval provides a range of values within which a population parameter may occur given a sample. In particular, a 95% confidence interval estimates a range for a parameter such that, if we were to take repeated samples, we would expect the true population mean to be contained within this interval in 95% of those samples. Confidence intervals are therefore used to estimate the amount of uncertainty with which a sample can measure a population parameter. This paragraph refers to figure 13.1, which shows a visual illustration of a confidence interval. There's a histogram on the top of the figure which depicts a population distribution and a vertical line that indicates the population mean. Underneath the histogram are 20 horizontally aligned bar plots corresponding to 20 samples of n equals 50 data points for each sample. And then we have error bars that indicate the 95% confidence interval around each mean. So in this simulation, the true population mean was within the 95% confidence interval in 19 out of 20 samples. It just happened to work out that way. Back to the text. Confidence intervals are widely used in statistics and yet are easily misinterpreted. Before explaining the math and implementation of confidence intervals, I'd like to introduce the two motivations for using confidence intervals and their associated interpretations. Motivation 1, to estimate bounds on a statistical parameter. An unknown population parameter, such as a mean or a correlation coefficient, can be estimated through a sample characteristic. But how certain can we be that that sample characteristic reflects the true population parameter? A confidence interval provides bounds around the sample characteristic that help us to understand how precise an estimate the sample characteristic really is. This is different from the standard deviation, as I will explain in the next section. The interpretation of a 95% confidence interval is that if we were to collect a large number of samples from the same population, 95% of those samples would have confidence interval bounds that include the true population parameter. In practice, it's not feasible to collect so many independent samples, so the confidence interval is used to help us evaluate the precision of our estimate. This is not the same thing as a p-value. Indeed, the p-value can be small while the confidence interval is large, and vice versa. I'll discuss the relationship between p-values and confidence intervals at the end of this chapter. Motivation 2, to perform statistical inference. Here, the idea is that if the H0 value is outside the confidence interval bounds, then the effect is considered statistically significant. For example, if a sample average is 0.5 with a 95% confidence interval bounds of 0.1 to 0.9, then we can say that the mean is statistically significantly different from 0 at a confidence level of 95%, which corresponds to alpha equals 5%. As I wrote above, confidence intervals and p-values are not the same thing. In fact, a confidence interval provides additional qualitative information that is not present in a p-value, as you'll learn later. However, confidence intervals can be useful for evaluating the statistical significance of sample characteristics when the data do not conform to assumptions of parametric statistics or when the H0 distribution is unknown. Confidence intervals can be calculated for any percent value. 95% confidence intervals are the most common, presumably to match the typical alpha threshold of 5%. Calculating confidence intervals. There are two ways to calculate a confidence interval. analytical and empirical. The analytical method is based on statistics theory and is deterministic, which means that you will always get the same result on the same data, but is defined only for certain statistical quantities, such as the sample mean or regression coefficient. The empirical method is more general in that it can be used to generate confidence intervals around any descriptive statistical characteristic, but it involves probabilistically sampling from the data and will therefore be different each time you compute it. Both methods have advantages and limitations. You will learn about both approaches in this chapter, but first I want to disambiguate confidence intervals from standard deviation. Section 13.2, Confidence interval versus standard deviation. Confidence intervals and standard deviations are sometimes confused, understandably so, considering that they share some conceptual interpretations, and the calculation of a confidence interval involves the sample standard deviation. So in this section, I will highlight their differences, starting with brief definitions to refresh your memory. Standard deviation. The standard deviation is a measure of the amount of variability or dispersion within a set of data values. It measures the average squared distance between each data point and the mean. A small standard deviation indicates that the data points are close to the mean, whereas a high standard deviation indicates that the data points are spread over a wider range. Confidence interval. Confidence intervals provide a numerical range within which we expect the population parameter to fall in a certain percentage of repeated samples from the same population. The wider the confidence interval, the more uncertainty there is about the estimate, but the more confident we can be that the population parameter is within that interval. Confidence intervals are different from standard deviation, but include standard deviation in the calculation. Differences. Here is a list of key differences between these concepts. Point 1. Standard deviation is a measure of variability within one sample, while a confidence interval provides a range that we expect our population to fall into in future samples. Point 2. Standard deviation provides information about the spread of individual data points around the mean, while confidence intervals provide uncertainty estimates of the true population mean. Point 3. Confidence intervals take sample size into account, while the standard deviation does not. To clarify, the standard deviation formula includes the sample size, but increasing the sample size does not necessarily decrease the standard deviation. In contrast, as the sample size increases, the confidence interval becomes narrower, reflecting increased precision in the parameter estimate. The upshot is that increasing the sample size will not trivially change the standard deviation, but it will shrink the confidence interval. This distinction is demonstrated in figure 13.2, which illustrates that increasing the sample size by a factor of 10 has no impact on the standard deviation while narrowing the confidence interval around the mean. This paragraph refers to figure 13.2, which visualizes the distinction between standard deviation and confidence intervals by manipulating the sample size. We see two panels, one on top, panel A on top, and panel B underneath. Both panels show a histogram in light gray, and on top of that are 5 lines drawn. We have a thick black line corresponding to the mean, that's at x equals 0 for both panel A and panel B. And then we have the black dotted lines showing the 95% confidence interval. And here we see in panel A, with a sample size of 100 versus panel B with a sample size of 1,000, the confidence intervals are actually closer to the mean, so closer to 0, in panel B with a larger sample size compared to panel A with a smaller sample size. And then we have two vertical dashed lines corresponding to one standard deviation around the mean, and that we see is visually nearly identical for panels A and B. In other words, in both panels, the distribution shape is the same, the standard deviations are the same, and the means are the same. But when we increase the sample size from 100 to 1,000, the confidence intervals became much closer to the mean with increasing sample size. Section 13.3, Analytical Confidence Intervals. In this section, you will learn the analytical method and its relation to the central limit theorem, and then in the next section, you will learn the empirical alternative. Here is the formula to compute the confidence interval of a mean. We have equation 13.1, which reads CI for confidence interval equals x bar plus or minus t star sub k times a fraction with s in the numerator and square root of n in the denominator. Most of the terms in this equation are already familiar to you. You should recognize the fraction term as the SEM, standard error of the mean. X bar is, of course, the sample mean. The new quantity in this equation is t star sub k. This is not a t-value that would result from a t-test. Now, some people use z instead of t star when the population sigma is known. I'll write more about this later. Instead, t star is the t-value associated with one tail of a t-distribution at the confidence interval level with k degrees of freedom. For example, the following code computes the t star term using a 95% confidence interval and a sample size of 20. Here we have in Python code a variable conf level equals 0.95, variable n equals 20, variable t star equals stats.t.isf, with the first input being the quantity 1 minus conf level divided by 2, and the second input n minus 1. Then we have our code, conf level, variable conf level equals 0.95, variable n equals 20, variable t star equals qt with 3 inputs. First input is the quantity 1 minus conf level divided by 2, df equals n minus 1, and then lower dot tail equals false. Back to the text. In this example, t star equals 2.093. The code below shows how to translate equation 13.1 into code, and also how to compute the confidence interval using SciPy. Here we have Python code where we have variable m equals 2.3, s equals 3.2, n equals 48, conf level equals 0.95. Then we have confidence interval from a formula where variable t star equals stats.isf with 2 inputs. First input is quantity 1 minus conf level divided by 2. Second input is n minus 1. Then we have variable conf int me, which is defined as a list containing 2 elements. The first element is m as the variable for the mean, minus t star times the quantity s divided by numpy square root of n. And then we have basically the same formula, except it's m plus the t star term instead of m minus the t star term. And finally, we have the confidence interval computed from SciPy. And here we have variable conf int SciPy equals stats.t.interval, inputs conf level, n minus 1, loc equals m, scale equals s divided by square root of n. And here's how that code looks in R. Here we have variables m equals 2.3, s equals 3.2, n equals 48, conf level equals 95. And then we have t star equals qt with inputs quantity 1 minus conf level divided by 2, df equals n minus 1, lower dot tail equals false. And then we have confidence intervals computed from a formula, and we have variable conf int me equals A variable with two elements. The first element is m minus t star times s divided by the square root of n, and the second element is m plus t star times s divided by the square root of n. Now, using these numbers, the 95% confidence interval is 1.37 to 3.23. There are several correct ways to report a confidence interval. You can describe the mean as a point estimate with an error, so x bar plus or minus 95% CI equals 2.3 plus or minus 0.93. You can also report the interval without the mean using various notations such as CI parenthesis 95% equals parenthesis 1.37 comma 3.23 or 95% confidence interval square bracket 1.37 comma 3.23 close square bracket. A few comments on analytical confidence intervals. Comment 1. Equation 13.1 does not require data to compute. You only need to know the mean, sample standard deviation, and sample size. Armed with this formula, you can compute the confidence intervals of published reports without having access to their data. That is a noteworthy difference from the empirical confidence intervals for which you need the actual data. Comment 2. Equation 13.1 shows why increasing the sample size decreases the confidence interval without changing the standard deviation. In particular, the standard deviation formula includes the sample size merely as a normalization factor, while the confidence interval contains a quote-unquote extra sample size term that reflects increased precision of the population mean with larger sample sizes. Comment 3. The analytical confidence interval is symmetric by definition. Symmetric confidence intervals are appropriate for symmetric distributions, but not all distributions are symmetric. Empirical confidence intervals do not have this constraint. Section 13.3.1 Assumptions of Analytical Confidence Intervals. The analytical formula for computing a confidence interval for a mean relies on the following assumptions. Independence. The data sampling procedure is independent, which, as you know, means that one observation does not influence other observations. This is ensured through random sampling. Normality. The data are normally distributed in the population. In part, this assumption is because the confidence interval is based on the mean and standard deviation, which are most appropriate for roughly normally distributed data. But the analytical confidence interval can produce nonsensible results for strongly non-normal distributions or small sample sizes. You will demonstrate this empirically in the exercises. Known standard deviation. If the true population standard deviation is known, you would use sigma instead of s in equation 13.1, and the confidence intervals would be drawn from a normal distribution instead of a t-distribution. In practice, this assumption is too stringent to be interpreted literally, so we use the t-distribution because it is slightly wider and therefore accommodates additional uncertainty. But this assumption can also be interpreted as sigma is roughly equal to s, that is, the sample standard deviation is a good approximation to the population standard deviation. Having a large sample size and a normal distribution helps with this assumption. When these assumptions are violated, the confidence interval may no longer accurately capture the population parameter in the stated proportion of samples. In particular, if the SEM is incorrectly estimated, the confidence interval can be artificially narrow. And when the sample size is too small, the confidence intervals can be so wide as to be practically useless. Imagine, for example, stating that the 99% confidence interval around the mean of a normal distribution is -4 to +4. That might be mathematically correct, but it's practically useless. when the analytical formula for confidence intervals is inappropriate, when you are unsure if your data meet the assumptions I outlined above, or when you want confidence intervals around other parameters such as variance or correlation coefficient, you can construct empirical confidence intervals. Section 13.4 Empirical Confidence Intervals. The analytical formula for computing confidence intervals is not ubiquitously valid. However, the concept of a confidence interval is sensible in a plethora of situations. That is, it makes sense to have confidence intervals for non-normal data, small sample sizes, and for other parameters such as proportion, variance, median, correlation, or the difference between two means. In these cases, you can compute empirical confidence intervals. The primary benefit of empirical confidence intervals is that they do not rely on assumptions about the population or restrictions about the shape of the distribution or the data characteristic under investigation. Indeed, regardless of the way you compute a confidence interval, the general idea remains the same. It provides a range of plausible values for an unknown population parameter based on the information in a sample. Section 13.4.1 Bootstrapping. I haven't yet defined bootstrapping, but it is related to concepts you learned in chapters 5 and 9 about drawing random samples to estimate a mean. Bootstrapping is a resampling technique that involves taking repeated samples with replacement from an observed dataset and calculating the statistic of interest on each sample. Let's start with a toy example. The table below is the result of bootstrapping from the set 1, 2, 3, 4 5 times and calculating the mean of each bootstrap set. So the true mean of the set 1, 2, 3, 4 is 2.5. Notice that the values can be repeated or omitted in the bootstrap samples, and for this reason, the bootstrap sample means can differ. Here we have a table with 5 rows and 2 columns. The left column is sample, and the right column is mean. The first row is the set 1, 4, 4, 4, and the mean is 3.25. The second row is the set 1, 1, 2, 3, and the mean is 1.75. Next row is the sample 1, 2, 2, 4. Its mean is 2.25. And then we have 1, 1, 1, 3. Its mean is 1.5. And finally, we have the sample 1, 2, 3, 4. Its mean is 2.5. Back to the text. The bootstrap means exhibit variability. Indeed, the means could, in principle, be as low as 1 and as high as 4, although we would expect the average of a large number of bootstrap means to be close to 2.5. Now consider another example using the set 2, 2, 3, 3. This is the same true mean as above. Again, we have a table printed in the text with 5 rows and 2 columns. The first row is sample 2, 2, 3, 3. Its mean is 2.5. The next row is 2, 3, 3, 3, and its mean is 2.75. Next row, 2, 2, 3, 3. Its mean is 2.5 again. Then we have the next row, 2, 3, 3, 3. Its mean is 2.75. And then the final row is 2, 2, 3, 3, and its mean is 2.5. Back to the text. Because the range of numbers in the sample is smaller compared to the previous example, that is, the standard deviation is smaller here compared to the previous example, the range of possible values of the bootstrap means is also smaller. Therefore, the distribution of bootstrap means will be narrower. This should make intuitive sense. The data values are closer to the sample mean, so we have more confidence that the sample mean is a good approximation of the population mean. Section 13.4.2 Bootstrapping Confidence Intervals. The analytical confidence interval assumes that you will obtain imaginary future samples. The idea of the empirical confidence interval is to assume that your existing sample is a good approximation of the population and therefore to obtain quote unquote new samples by repeatedly resampling from the existing sample. The 4 steps below describe how to create empirical confidence intervals using bootstrapping. Notice that this approach is algorithmic and iterative in contrast to the analytical formula. Step 1. Draw a sample from your data with replacement with the same sample size. This is called a bootstrap sample or a resample. Importantly, because the sampling is done with replacement, the bootstrap sample is unlikely to have identical descriptive characteristics as the original sample, even though the sample sizes are the same. Step 2. Calculate the descriptive statistic of interest, so the mean, median, variance, correlation, etc., of this bootstrap sample and store that value in a variable like a NumPy array or a vector. Step 3. Repeat steps 1 and 2 hundreds or thousands of times to generate an empirical bootstrap distribution of your sample descriptive statistic. Step 4. Take the 2.5th percentile and the 97.5th percentile of the bootstrap distribution. This is the empirical 95% confidence interval. Exercise 6 will ask you to translate this description into a Python or R function, and exercises 6 through 9 will prompt you to use that function to explore empirical confidence intervals in a variety of situations. Section 13.4.3, Comments and Assumptions. There are several points I'd like to make about empirical confidence intervals. Assumptions. Because bootstrapping draws samples from your measured data, there is no need for assumptions about the shape or the characteristics of the population from which those samples were drawn. However, there are 2 key assumptions underlying bootstrapping for confidence intervals. Assumption 1. Your sample is representative of the population. The confidence intervals are computed from your sample data and therefore cannot be used to generalize a population for which the sample data are not representative. Assumption 2. You have enough data for a sufficient number of bootstrap samples. Quote unquote, enough is always a tricky word in statistics, but let's imagine an extreme case with a sample size of 3. There are exactly 10 unique ways to sample with replacement from this dataset. That's not enough variability to create a distribution. On the other hand, with n equals 30, the maximum number of ways to sample with replacement is more than 10 to the 16, which is way more than the approximately 10 to the 3 random samples that are typically used in bootstrap confidence intervals. On the other hand, n equals 30 might be too small a sample to be confident that this sample is representative of the population, and this in turn depends on the sampling and measurement methods, variability in the sample, and so on. Confidence interval width and sample size. Empirical confidence intervals generally decrease with increasing sample size, but not in a deterministic way as with analytical confidence intervals. Due to the inherent randomness of the bootstrapping process, the bootstrap samples become more representative of the population as the sample size increases, and therefore the spread of the bootstrap estimates tends to decrease. Number of resamples. There is no exact number of resamples to produce a stable confidence interval. It depends on the complexity and the size of your data, as well as on the statistic being estimated. Increasing the number of resamples enhances the precision of the bootstrap confidence interval, but only up to a point. I'll have more to say about this issue in Chapter 16 on permutation-based statistics. For now, you can consider Figure 13.3, which shows that the empirical confidence interval is quite stable across a range of resamples, and the data in this case were 50 samples generated as mean-centered x squared for x, normally distributed according to a standard normal distribution. Of course, this is just one example using simulated data, but myriad experiences in empirical data confirm the validity of this conclusion. 1,000 resamples are sufficient for most applications. This paragraph refers to Figure 13.3, which shows an illustration that the number of resamples has little impact on the empirical confidence intervals. Here we see a plot showing around 25 or 30 horizontal lines corresponding to confidence interval widths with the number of bootstrap samples on the y-axis and the data value on the x-axis. So in the center of each horizontal line is a small white box showing the bootstrap mean, and the width of the line corresponds to the confidence intervals. And what you see is that with increasing bootstrap samples from 10 up to 5,000, the bootstrap confidence intervals are roughly the same within some reasonable amount of error, with one exception of the very lowest line corresponding to the smallest number of bootstrap samples. That one's a little bit off, but most of them are roughly the same. The conclusion from this figure is that increasing the number of bootstrap samples above around a couple hundred up to 5,000 doesn't really appreciably change the confidence interval limits. Back to the text. Non-deterministic. Because bootstrapping is a random process, the same algorithm on the same data will produce different confidence intervals each time the procedure is run. Hopefully, repeated confidence intervals are comparable to each other. Fortunately, the law of large numbers helps ensure that a sufficiently large number of bootstrap sample statistics will be a good approximation of the true confidence interval bounds. Symmetry. Symmetric confidence intervals are not guaranteed. If the population is normally distributed, the confidence intervals are likely to be roughly symmetric, but this would be a result of the data distribution and/or the central limit theorem. A situation where you will find asymmetric empirical confidence intervals is with data that are close to a boundary. For example, many countries have minimum wage laws, which means that a confidence interval around the average salary of a service industry job is likely to have a lower confidence interval boundary closer to the mean compared to the upper confidence interval boundary. You'll see examples of this in the exercises. Bootstrapping confidence intervals has several advantages over the analytical method, but it is not a magic bullet guaranteed to work. Very small sample sizes or data with extreme outliers can still make empirical confidence intervals unreliable or uninterpretable. Section 13.5, Confidence Intervals and Hypothesis Testing. The idea of hypothesis testing is to evaluate the probability that a parameter could be observed due to sampling variability or noise while there is no true effect. For example, if we perform a t-test to evaluate whether a sample mean is significantly different from 0, the question is whether the population mean is 0 and our sample mean is non-zero simply due to sampling variability. I hope you see where this is going. We can use confidence intervals to perform hypothesis testing. Here's an example. Imagine we have a sample with x bar equals 1.3, s equals 3, and n equals 48. The 95% confidence interval around the mean is 0.37, 2.23. This range excludes 0, which means that 95% of future samples from this same distribution will also exclude 0 in their confidence intervals. In terms of hypothesis testing, we therefore infer that it is unlikely that the true population mean is 0, i.e., the sample mean is statistically significantly different from 0. As a counterexample, if S equals 5.2, while the other characteristics are the same, then the confidence interval is minus 0.21, 2.81. This range includes 0, which in terms of hypothesis testing indicates that the population mean could be 0, i.e. the sample mean is not statistically significantly different from 0. I calculated those confidence intervals analytically, but you could also use bootstrapping, which means that confidence intervals can be used for statistical inference in non-normal distributions and for data characteristics that have no known H0 distribution. You'll see several examples of this in the exercises. Section 13.5.1, Confidence Intervals versus P-values. P-values and confidence intervals are two statistical techniques that can be used for hypothesis testing, but they provide different types of information and are interpreted differently. As a reminder, p-value is a probability that an observed effect in a sample could have resulted from random chance in a population where there is no effect. Confidence interval provides a range of values that is likely to contain the population parameter from repeated sampling. They do have similarities. Neither is a measure of effect size. A tiny effect and a huge effect could have the same p-value, and both could have confidence intervals that exclude 0. You've already seen examples of this in previous chapters, and there will be more examples in the following chapters. Furthermore, both p-values and confidence intervals are sensitive to the sample size such that very large samples can make small and possibly unimportant effects statistically significant. The way to think about their differences is by the questions you would ask of both methods. So, p-value. Is this effect statistically significant? Confidence intervals. What range of values might include the population effect? In conclusion, p-values and confidence intervals are related but distinct concepts. They can be used together to provide complementary information about the data. You'll have the opportunity to explore this in exercises 10 and 11. Section 13.5.2, Confidence in Confidence Intervals. Consider Figure 13.4. Figure 13.4 illustrates the concept that the size of the confidence interval provides information beyond whether it overlaps with 0. We see here a set of 4 box plots with small squares and then error bars extending both above and below each of the 4 boxes, indicating the 95% confidence intervals. On the y-axis, we have a range from 0 to 10, and there is a horizontal dashed line at 0. And then on the x-axis, we have 4 tick marks, A, B, C, and D. Now what you see here is that the means for A, B, and C are relatively far away from 0. The error bars in A and C are large, and the error bars in B and D are small. And the mean of D, so the location of the box, overlaps with y equals 0. Furthermore, the error bars, again indicating 95% confidence intervals, exclude the 0 mark in A and B and include 0 or overlap with 0 in C and D. Back to the text. Assume that the boxes correspond to means. The horizontal line at y equals 0 corresponds to the H0 value, and the bars correspond to 95% confidence intervals around those means. Parameters A and B are statistically significantly different from 0, and parameters C and D are not. However, we can be more confident in findings B and D compared to A and C. Perhaps there is less variability in the data, or perhaps the sample sizes are larger. As a reminder, the error bars in A and C are much larger compared to the error bars in B and D. Parameter C could be statistically significant in a replication study with a larger sample size. Or perhaps parameter A could become non-significant in a different sample that had slightly higher variability. Here's an example to make this more concrete. Imagine you are a medical researcher who is testing the efficacy of a new medication on treating the flu in elderly. Footnote: although the flu is usually a minor inconvenience to young, healthy people, it kills hundreds of thousands of people each year who are very old, very young, or immunocompromised. Back to the text. The medication has no side effects, but is expensive to manufacture. If the results of your study were parameter D, you would conclude that this drug is not worth using because of its expense and clear lack of efficacy. On the other hand, had the study produced parameter C, you might conclude that the medication warrants further research. Perhaps the medication could be improved, or perhaps the efficacy is high for an identifiable subgroup of individuals while being ineffective for others. The point is that although the label of statistical significance is binary, there are many situations where inspecting the confidence interval can facilitate a more nuanced interpretation. Section 13.6, Exercises. As you know, I direct you to my YouTube channel for explanations of the exercises. End of chapter 13.